Good afternoon. My talk is about the action recognition from landmark data. The landmark data here means the you can see that on the left. It means the key points or selecting joints distributed on the body, and there are researchers in 1970s found that people, as humans, we can easily tell the action from a sequence of landmarks or skeletons, like the other two images. On the left, we can see that maybe the person is picking something.
Pocket. In your pocket.
Okay. Picking something from the on the ground, and the other one maybe someone is catching a ball or shooting one, maybe. So so that our target is to teach the machine to recognize these actions like what we humans can do. Actually, the action recognition have many downstream applications, such as the natural interaction between human and objects, between human and computers, and motion sensing games. And another important application is the anomaly detection. The start from the CCTV cameras. The surveillance staffs can be noticed by the machine and react quickly to the conflicts or some other emergencies. And for the self-driving car, the driving system is designed to locate people so as to avoid hitting into them. But the action recognition actually can help the driving system to understand the human actions and maybe predict the next steps. So in short, the action recognition is to assign action labels to video clips. For most of the time, our data is 2D RGB data, like we see at the left, and we can, since people find that the pose estimation can estimate landmarks on the body, and people can just tell the action from looking at these landmarks. The pose estimation algorithms since then become more and more popular. By definition, the landmark data is very robust against the appearance or lights changing or light variation or even the occlusion. They are simplified from the RGB data, and the data dimension is reduced significantly. Also, given that the people's appearance information is no longer exists in the landmark data, it's somehow the privacy can be somehow protected in public places under the universal CCTVs. However, the pose estimation is still a very tough problem. So, and the location of the landmark is not very accurate enough. We can also see some errors in these videos. Yes, and another problem is that if we extract landmarks from the videos, we ignore the objects we interact with, so we actually lose a lot of valuable information. and moreover, if we for some fine-grained actions like we stretch something, if we don't have a landmarks on the finger, the recognition system may also fail. Even though most of our videos are 2D RGB captured by 2D RGB cameras, the human body is natural in 3D space. So people decide the other two cameras, the marker-based system and the depth cameras, to capture the 3D landmarks. The marker-based systems use a lot of shining markers on the body, and there is a series of cameras around you to capture the action, so that they can provide very accurate landmarks, accurate location of the landmarks. But the system is very expensive, and so the people may prefer to use the depth cameras. It's much cheaper and much popular nowadays. But there's a problem for these two 3D solutions, because they use the infrared, which is not very functional in the outdoor scenarios. So to recognize the action, the main challenge is to decide discriminated features for spatial structure in each frame and temporal dynamics across the time. So we use the path signature features here. The reason that we use path signature feature is that the signatures can determine the shape of the trajectory and provide us a large amount of nonlinearity. And also, the signature is invariant on the no matter how far you perform, and will have a fixed dimension of features no matter how long you perform the actions. So these are our solutions for the action recognition. So for the spatial structures, we divide joint pairs and joint triples as pathlets, and then we extract the signature over these pathlets. These features have very clear physical meanings, like the displacement of pairs and the enclosed areas of triples. And then we concave all these features to form the spatial features. And for the temporal dynamical features, it contains two parts. The first one is extracted from the evolution of each landmark. Evolution of each landmark, and the other one is extracted from the evolution of the spatial features we extracted we mentioned in the previous slide. So we call it the spatial temporal paths. So these two features concave together to form our temporal features. So using this, finally we concave all these features to an input, input these features to a linear network, a linear fully connected neural network. It contains just two layers. So and the activation function is identity. So it's just a linear network, in linear model we are using here. And we evaluate our methods on 4 typical benchmark data sets. These data sets are vary from using ground truth, that means a label just annotated by humans. Using ground truth pose, they are vary from using ground truth pose to using estimated pose. They are vary from 2D landmarks to 3D, and also they are vary from just single person actions to mutual actions. And also they are vary from the small in sample size to a large scale data set. So we can see that all these results show that our methods using the path signature achieve the very high accuracy, even in comparison with some recent deep learning methods. Okay. Recent RNN or LSTM methods. So actually we make further steps to understanding these actions. That's the advantage of our methods compared with the deep learning method, because in the deep learning models you may very hard to understand what the feature automatically learned by the deep learning models. But given that we're just using a linear network, the output of the network is just a weighted sum of all the extracted features. So we can get the degree of importance of each features for each class. So we can see here for the spatial structure, the top 10 most discriminated triples, the triangles, we are shown here. We can see some very reasonable results here. For example, for the action of catch, the triangles between the right and the shoulders is more discriminative than the others. And for example, if we playing golf, we actually swim using both our arms. So the triples between the arms are very active. And there is also the running. We can see that the triples between our legs is the most discriminated one. And for the temporal dynamics, we also generated heat maps to show the degree of importance of each landmass. We can see that we can see that these two similar classes, climbing step and running. For the climbing step, you can see that the knees are highlighted. And for the running, we can see that the ankles are highlighted. And that's all. Thank you. And that's the important reference. And this word is there are many co-authors. Yes, shown here.
Thanks, Weixin, for his talk. And yeah.
Sorry, you might have mentioned it, and I might have missed it. So these sensors sometimes give you angles of joints, and sometimes give you positions. Which type of data do you use, the angles or the positions?
Just the positions.
Position, not the angles.
Yeah, right.
And did you have to do any pre-processing for the values they give you, the raw data, or was it just use the raw data?
Yeah, we need to do the pre-processing of the data, because we need to center the skeletons, because they may happen in different places in the video. So we need to center it in using the necks or the belly landmarks. Yes.
Any reason why you use linear networks if it's linearly separable, then why not one of the simple classifiers?
Sorry?
You mentioned you use linear.
Yeah, we use the linear network.
So if it's linearly separable, why didn't you use one of the simple classifiers? Why? Is there any reason?
Because actually the network we are using is very simple. It just contained one hidden layer, and yes.
So the question is, if you want to do the linear classification, why do you just use the analytic formula for the linear classification, rather than putting into the neural network with the identity activation function?
Actually, we also leverage the advantage of the some deep learning techniques, like the training with backpropagation, and can like using the mini bench strategy. So we adopt this strategy instead of just using the SVM or some simple classifier.
I think maybe part of the reason is the dimensionality of the feature space, right? It's very high.
Yeah, it's also
Standard SVM can't handle. Is there any more questions?
The message that we seem to be getting this morning is that in most cases you throw away the time information. So Terry showed us a 3 that was drawn quickly and slowly, and they look the same. And if I give you a hand gesture and I do it slowly or quickly, it looks the same. But you had some jive dancers there. If you asked them to dance that dance at a quarter of the speed, it would look completely different. So is that not a case where you need to preserve the time information and make correlations with that as well?
Can I answer that first? Because I've been quoted inaccurately. Okay, I did not say you ignore the time variable. I said you ignore the rate at which you acquire the information. So it's very easy, if the time variable is important, to put it back as another dimension to your data, right? And in finance, for example, you might have several time variables. One might be the volume of trade, one might be the volume of volatility, one might be real time. I mean, there are often lots of different time scales. They can all be there. What I actually said is that it doesn't matter how quickly you measure the sampling points, the missed data points that you can measure. Once you've got your curve in space-time, you can sample it at different rates without losing what it's about. So, for example, the context here of that really would be to take frames out of the image. If you only had 2/3 of the frames and they were randomly selected, that would be okay. I didn't really say time didn't matter. I said the way you collect the information in time doesn't matter, which is subtly different.
Yeah.
Sorry. No, sorry.
it's okay. It's a very good question. Actually, in our design of our feature set, we consider these problems because maybe sometimes we want the speed factors to involve, and sometimes we don't. And so for the tempo, sorry for not going into very details in this presentation, it's because it's short. You can see it in our papers for some detailed information. But here, actually, we use a time dimension here. So with a time dimension, actually the extracted path signatures contain 2 parts. One is associated with the speed. Another is invariant under the speed variation. So actually we have 2 parts here.
Thank you.
So thank all the speakers again.